Hi guys, here back again with another interesting project. This time, high voltage linear DC power supply. Um, as you might be aware from my watching my other videos in my channel, I have quite a bit of low voltage power supplies with varying amounts of output current capability, but I don't have any high voltage power supply. The highest voltage that my one of my power supplies can go is this guy, which is able to go to around 60 volts. From dealing with a few other projects, I've come to require a high voltage power supply in the range of 0 to 800 volts. And this project will basically try to address that deficiency that is in my lab, which is basically constructing a high voltage power supply from 0 to 100, from 0 to 800 volts. Recently, I've been lucky to acquire a couple of transformers that will allow me to construct this linear power supply. The one that I'm going to be using for this project is this 120 volts to 600 volt one-phase transformer made by Hammond, and I will be using this feeding 120 volts on the secondary here and getting 600 volts RMS, and when rectified it will give me a little more over 800 volts, so I should be able to use this for the project. But before I do that, I'm in the testing phase of this project, and in the moment I'm using this other transformer, a little smaller than the one I showed you. This one is a 50 VA 120 to 240 volt transformer. So I'm feeding 120 volts here. I'm getting 200 volts, 240 volts on this here. So I'm using it basically to test a proof of concept of my project before I go ahead and then do the 0 to 800 volt power supply. And also I don't have the required high voltage transistors at the moment, so I have transistors that are capable of going to 400 volts, so those are the ones I'm using for testing. So going back to the actual circuit of the project, I have here, this schematic will also be used for the final project, but at the moment I'm using it to test various components of the project to make sure that this circuit is stable enough to operate the output without any ripple from 0 to 150 from 0 to 800 volts, but at the moment I'm doing it from 0 to 150 volts. So if we quickly describe the circuit, basically this is a linear power supply. It's not a switching power supply, and I want a linear power supply because in terms of noise and in terms of ripple, linear power supply is much more desirable, so I will be using that. And of course the transformer I have is a low frequency transformer, so that also limits my application to be linear power supply. So that is one of the reasons I'm constructing or designing a linear power supply. So if we quickly describe the circuit, this is working really quite well at the moment, at least until 150 volts to about 200 volts. And I think I should be able to scale this right up to 800 volts once I receive the high voltage transistors. So as I have shown you here, I have the 120 to 240 50 VA transformer. It feeds a bridge rectifier, KBP307. I haven't decided if I'm going to use this in the final, but at the moment it's working quite well. And I have a bleeder resistor here, and a bit of ceramic capacitor here to filter the output, and a bulk capacitance 200 microfarad 250 volt capacitors. And just in case of the output gets shorted when I'm testing here, this allows me to limit the current to something to a safe level. So I have a 100 ohm resistor on the just before it goes into the regulation part of the circuit. For this application, I am using MC34072 optimized for single supply operation. As you can see, I'm operating it from 15 volts to ground, and this is a fast high slow rate oil pump capable of responding sufficiently fast to allow the regulation to take place while the load changes on the output side. So it's quite capable oil pump, but on the final circuit, I think I might use a little faster than that even. I think I have in mind the AD823 from Analog Devices, so I will probably use that for the final implementation of this project. Right now, this part of the circuit is not built. This generates the required reference that we can use to vary the output voltage from 0 to 800 volts. Right now I haven't implemented this, so I'm just using my bench power supply to generate the reference voltage, just 10 volts at the moment. But when I'm doing the implementation on the final project, I should be able to construct this part using a reference voltage TL431 to give me the required 10 volts here from a 15 volt supply, which I will also design using another low power transformer, which I have, which I will show you in a second. Actually, I can grab it. So the one that I have in mind is this little transformer here. It's 120 volts primary, 12 volts secondary. This should allow me to generate the required low voltage for the control side of the circuitry, so I'll use this for the final project. But at the moment I'm just powering it from my bench power supply for the control part of the circuit. So continue with the description. So this is a little bit interesting circuit where in order to regulate the output, we're going to use high voltage transistors. These are capable of doing 400 volts, and I think they're 5 amps. So these are quite capable transistors. The BUT11. Using them in Darlington configuration because high voltage transistors have very low gain, so one is not enough. So I'm using two transistors in Darlington configuration to give me the required beta, so that I don't dissipate a lot of power when I'm when I'm regulating the output, as you can see. Because if you only use one transistor, then this resistor has to be smaller. So if it's smaller, then it's going to draw quite a bit of current through here while the regulation is going on. So in that case, this needs to be a power resistor, and then just it's not pretty. So that's why I opted to use Darlington. So just use two transistors. Yeah. So in my final circuit, I'll use another transistor. I think it's the I don't know if I have the name right, but it's the 2AC3438, I think. It's capable of doing 1.2 kV at 4 amps, so I should be able to use those two to generate the voltages for the regulation part of when I'm doing the 800 volt supply. And I'm also using here the IRF 710 here, but I'll replace this when I'm doing, because this is can only do 500 volts. When I'm doing the 800 volt supply, I should be able to switch this by another transistor, by another MOSFET. I think I should be able to use the I have it here. It's this transistor here. I don't know if you can see. This is capable of doing this is the IRF BG30. This is capable of doing I think a couple amps at 1000 volts, so I should be able to use this in the final circuit. But for now, for testing purposes, I'm using IRF 710. Might have when I implement this using this transistor that I just showed you, might have an issue with oscillation because this has quite a bit of gate capacitance. So we'll have to experiment with that to make sure that this circuit won't oscillate while it's doing the regulation, because the gate capacitance of this MOSFET is quite low. So this is an interesting circuit, as I said before. So in order to regulate the output, what we'll do is, let's say for example, if this potentiometer is set to here, which means 0 volts, then by op-amp action this will be 0 volts as well. And if that's 0 volts, in order to do that 0 volts, this has to be basically turn on this transistor completely on. That means this output is high, so close to the 15 volt rail. And if this transistor is completely on, then this point is at ground. And if that point is at ground, then all of the current just passes through here, because this base emitter junction of these two transistors are turned off. So that is when this spot is turned off all the way down here. So we should get 0 volts on the output. And when this wiper of this potentiometer is all the way at 10 volts, by op-amp action again, because of negative feedback, this will be 10 volts. This will be 10 volts as well if this is 10 volts. And this one, by, we don't know what's going to be, we'll measure, but somehow it will allow, by giving the right voltage, turning on this transistor maybe completely off, or or partially on, to allow enough current to go into the base of these two transistors, maintaining the required voltage. For this case, the maximum voltage output is close to 150 volts, so somewhere around there. So that is how the circuit operates. And if you noticed, the negative feedback from the output is fed back into the positive of the op-amp. Normally you would see in a lot of negative feedback circuits, it's the negative, the inverting input that's used for negative feedback. But in this case, because we're using it in opposite way, right? Like, because the way it works is it's basically opposite to a normal negative feedback. In order for the regulation, the overall feedback to work, this has to be fed back to the positive input of the op-amp. And you can analyze the circuit to see why that's the case. Because if this goes high, that means it's going to turn on this guy. That means it's going to drag this one down. That means this has to be 0. So in order for us to regulate, then this has to be fed back to the positive input, not the negative input of the op-amp. And to allow the circuit to work stably, I have 150 picofarad of composition capacitor here, and also local negative feedback here for another stability regions, 150 picofarads from the negative input right to the output of the op-amp. So that's how the circuit works, and I will go ahead and show a description of the circuit built in a breadboard. So let's take a look here, quickly describe the circuit before we test it. Here are the two BUT11 high voltage transistors in Darlington manner. The rectifier I showed you, the transformer here, fed back through here, feeds back the circuit through this wire to here, back into the input of the rectifier, the AC input, and the DC bus is this pin and that pin. This pin is grounded, so the ground rail is on this internal bus here, and the external bus is a positive, so I have connected it through another wire here. I don't know if you can see it. There you go, into here. And so how this works is these two buses, the internal bus is both ground, and the external bus is the high voltage input after the rectifier. And there's the FET, the IRF 710, and the op-amp, the MC34072, single supply capable op-amp, very fast, so you can see. And then this is the feedback, this is the output, loaded by a 10k resistor. I think it's a 1 watt resistor, to allow me to extract some current, from this rail here, so that the minimum load requirement of this circuit is basically satisfied. It could be lower than 10k. I think it's a couple of milliamps should do. Basically, a minimum load in a regulator circuit is always required, so that to allow the circuit to do its regulation properly. So that's basically it. and quite a bit of filtering, as you saw in the schematic. Lots of two big 100 microfarad capacitors here, high voltage, on both rails of this circuit to allow filtering after the rectifier, and also on the output a couple this is a 10 microfarad and this is a 68 microfarad high voltage capacitors here at the output to give us stable output, and few ceramic capacitors here to allow high frequency decoupling of the circuit. So let's go ahead now and power the circuit up and test it to see if it works. Okay, I'll set this up and I'll be right back. Okay, so the circuit is back. So let's describe what the points that I'm monitoring. This meter and this meter are measuring. So this meter and this meter are measuring the two inputs of the op-amp here. Reason is, in order for me to verify that the overall negative feedback and the circuit is working stably, these two voltages need to be equal. And then since I will be varying this using this potentiometer here, to get my variable supply, so I'm going to need to monitor these two to allow me to see whether the op-amp is working correctly. So if by op-amp action, the op-amp will do whatever it can on the output to make sure these two inputs are the same. So in terms of voltage, the same, so that the overall circuit is working correctly. So I'm monitoring these two. So while we're varying this potentiometer, you'll see that these two voltages will be equal, and we'll see that the circuit is working correctly. Next, I'm using this meter just to do general checkup before I power the circuit up. So this one is just it's one side is hooked up to ground. This one allows me to go and measure, poke around in the circuit to make sure everything is working correctly. And this one is measuring the so this meter is measuring these two, the voltage from the base of this transistor all the way to here. So we should be able to see the while the regulation is going on, the voltage varying all the way from 0 to somewhere around 1.2 1.3 volts, because this is Darlington configuration. So so we'll be able to see that changing. And going back here, as I said, my reference input into my potentiometer to allow me to vary the voltage. This meter is measuring the DC rail, the unregulated DC rail. So basically it's measuring this rail here. So it's measuring this rail here. And so that's what this one is doing. And my supply for my op-amp, this one is not hooked up. It's 5 volts, but it's not hooked up to anything. So let's just turn that off. And my output. So this one will show me the regulated output. So basically it's measuring the voltage right here. And like I said, I have a load of 10K here. So whatever voltage you will read on that meter, divide it by 10 to get the current. That's how much current we'll be extracting from the rail. So let's just adjust so it doesn't glare. And that's basically it. And like I mentioned, this is a transformer I'm using. Primary is hooked up to here. I have my variac, where I am able to vary the input voltage into that transformer to allow me to safely bring up the voltage. And basically that's goes straight to here. And yeah, so this is basically it. So let's go ahead and power the circuit. A word of caution and safety tip here. If you are going to build this circuit on your own, please take care. Make sure to take safety precautions to make sure that you don't hurt yourself, because there's a lot of energy here to cause serious harm or kill someone. So basically, make sure that if you're going to build this, to follow safety precautions around high voltage. And remember, there will be almost 200 volts across here, so the circuit is is high voltage here, so we have to be careful while we're doing this. So what I'll do is I will turn on my variac. So just this meter turned off, so let's just turn it back on so it doesn't measure. So I'm gonna turn on my variac. It's always set down. It's just down, so There we go. My variac is turned on. So let's check here. See how the DC bus comes up. As you can see, there we go. The DC bus comes up. We're gonna go all the way to 200 volts. Adjusting. Let's go. Somewhere around there. So yeah. So that's basically the 200 volt scale. So I don't want to go above that, so that I get enough resolution. So that's what I have on the input. So that's before here. So basically that's this rail here basically. So actually this rail here to be exact. And I'm measuring on my oscilloscope here. Channel 1 is measuring the DC output, so it's measuring the DC output here. Sorry, the DC output here. And channel 2, which is the blue waveform, is measuring the ripple. So it's, the output is AC coupled to allow me to see the ripple on the output. And that analog oscilloscope over there is measuring the basically it's measuring this point here, the base of that IRF 710, just to see how the op-amp is doing its regulation. So we'll see some switching waveforms as it's going. And yeah, so basically that's about it. So now let's put all of this into one shot so that you guys can see the while the circuit is changing its the dynamic behavior of the circuit while I adjust the output voltages in this potentiometer. So I'll move this meter here so you can see the actual output voltage. So here we are. So observe as I vary the this potentiometer, which I'll put in the shot, the output voltage, the base to emitter voltage of the two transistors, the regulating transistors. This one is just not measuring anything. This one and this one, positive, negative input of the op-amp, positive input of the op-amp. So let's take a look. So let's go ahead. There we go. So we got something right there. You go. So now you can see that this matches with that one. So that means the circuit is working correctly. Our output is 5 volts, and you can see that it's not varying much, and I'll show you in the scope in a moment. And this one is 0.9. So the VBE of the two transistors added up comes up to somewhere around almost 1 volt basically. That's the DC rail. And take a look at the DC rail as it gets loaded. It's gonna sag a little bit. So yeah. And let's take a look at the output waveform. There you go. So channel 1, as you can see, it's measuring the output, so around 4 volts, right? It's 5 volts because we are in a 50 volts per division here, so resolution here is not going to be good, but you can see that the ripple on channel 2 is very low, as you can see, pretty much 20 millivolts peak to peak. So let's go ahead. Let's keep going. So there we go. We are right now, the output is at 40 volts. So we're extracting, like I said, since we have 10k load, 4 milliamps from the circuit. And you can see that this op-amp, the op-amp inputs match. So let's go here, one level up. So 1.3, 1.3. So that means the circuit is working correctly. And our ripple stays really low. In fact, actually it went down to 14 millivolts peak to peak. And you can see our DC rail is 41 volts. And yeah, so let's keep going. So let's test it all the way to 150 volts. So what I'm going to do is I'm just going to go to 150 volts. There we go. Right about there. You can see 150 volts on the output. So which means we're extracting 15 milliamps. 4.874. Well, this one I think I should just do it auto. So let's just do it auto. You can see that 4.8. That's the base emitter voltage of the two transistors, 150 volts. You can see that our rail, unregulated rail, got loaded, and our ripple went up a little high since we are extracting quite a bit of current now, about 15 milliamps. And yeah, so you can see that it's pretty low. So, and our output, DC output, as you can see, is 154 volts. So as you can see, this regulator works nicely, and all I have to do now is to scale it to a higher voltage from 0 to 800 volts by scaling all these parts correctly. So by scaling all the capacitors, the Darlington transistors, and the MOSFET, so I should be able to scale this up to 0 to 800 volts power supply. So this is the demo, and yeah, so what we'll do is we'll just see if we can put everything in one shot. Well, this is wiring. You can see now at the low end of the scale, like below 1 volt, the circuit is a little unstable, as you can see. Reason is because the feedback, this voltage needs to be divided up, to really small, so so below 1 volt, so it's not going to be that stable, but who cares, right? What we like to use this is above, because it's a high voltage, so it shouldn't matter. But even now, it doesn't. Let's take a look. Let's just test it at 1 volt. Let's take a look how it operates. Let's go down. I don't have a 10 turn pot, that's why it's hard to adjust this. So let's take a look somewhere. Let's test it at 1.6 volts. You can see it's not bad. It's a little stable. You can see that 51 millivolts. That means the op amp is working. You can see we have a bit of ripple, not much actually. So even the circuit is, all the way to 1.5 volts. It's great. It's actually quite impressive. So that's basically it. So once I have built the other version of this power supply, the 0 to 800 volts, I should be able to make a tutorial, basically building it from, actually doing a tutorial how I calculated each value of these resistors and how this whole circuit operates, and how some engineering design decisions that I need to make in order to make all this whole thing work. So I should be able to make a detailed tutorial in an upcoming video. So take care. If you enjoyed this video, please subscribe and tell your friends. And yeah, so we'll have quite interesting projects upcoming. Take care, and I'll see you.